So to start today off, we're going to go over number 6, which was really part of day 1. And this says to find y double prime implicitly. So what's the difference between implicit and explicit differentiation?
Implicit is when you're having y as well.
So implicit is when y isn't y equals, but it's in the middle of the problem. And that's really all there is to it. Now, when we differentiate with respect to x, which is what we're doing, anytime we get to a y term, we're going to have to remember to do the chain rule. So what was the first step of implicit differentiation? Remember, we had 4 steps. Okay. So we take the derivative with respect to x of the left side and of the right side. And I just said this, but remember, when you take derivative with respect to x, that's just like normal when we're doing x terms. So the derivative of x squared, that's just 2x. But since I'm taking derivative with respect to x of y squared, we do get 2y, but then you've got to multiply by dy over dx. And so you have to do this because y is its own function. So it's kind of like the chain rule. You do the power, and then, like using the analogy of the M&M, the chocolate is the y value. Yes, actually.
On the right side, why did you put d over d?
Oh, that's just me being silly. That should be an x.
Okay.
Whoa, that was a big. Yeah. I was doing too many. I'm going to do it again. All right, d over dx of 25. Thank you for catching that. Okay, so what is the derivative of 25? 0. And now what do I have to do? Yep, I got to get all the dy over dx terms on the left side. Well, good news is this is already on the left side. Okay, and that means I need to subtract the 2x. And so what does dy over dx equal? Negative 2x over 2y. So this was a pretty simple problem. There wasn't any factoring I needed to do. And in fact, I could go ahead and cancel out those 2's, although if you didn't, that would be fine because the answer would be the same. So this is, I really shouldn't be, I'm going to back that. This is our first derivative. This would be like y prime. Okay, I want to let you in on a little secret. This is what shape? What shape is x squared plus y squared equals the radius squared? It's a circle. When you do implicit differentiation on a circle, you will always get negative x over y every single time. Because every circle is x squared plus y squared equals a number squared. So the number doesn't ever matter because when you take derivative of that number, you get 0. All right? You still need to do this. This is not something you can just write the answer down, but at least now you know what your answer is always going to be. Okay. I'm not done because what I'm really trying to find is y double prime. And what this is going to look like is d squared y over dx squared. Okay, so the way we're going to do this is we're looking at our problem right here. I'm just going to take derivative again. That's how we've been finding second derivative. That's what I'm going to do here. So it's still with respect to x, so d over dx of the left side, which would be dy over dx, equals the derivative with respect to x of negative x over y. All right, so if you look at this and you're really just thinking like multiplying almost, you're going to get this d squared y. Think about it, d squared y, dx dx, that's dx squared, where really what you're squaring is the whole thing dx, but I'm not going to write parentheses there because this is the notation. But I want you to understand, all this is the same thing as y double prime. Okay, so that means all I have left is taking the derivative of the right side. Well, the right side's a quotient. So what do we need to do? The quotient rule, all right? So remember for the quotient rule, we need to take the derivative of the numerator, that's -1, and we need to multiply that by the denominator, and then minus. Then you just switch them. So now I'm just going to write the numerator. I'll put that in parentheses so I have the minus minus, it's obvious. And then what's the derivative of the denominator? 1 dy over dx. And then this should all be over y squared. All right, there's only one teensy weensy little problem. And that is, you can't have dy over dx in your answer. All right, but this is way easier to fix than you're probably thinking. Okay, so first of all, let me go ahead and rewrite the problem. I'm going to write it a little bit bigger. And I'm just going to write -1y is -y. You don't have to do this simplification, but this is what I would consider easy, hopefully foolproof. All right, minus -x. That would be the same as plus x. And the only other thing we need to do is we need to put dy over dx. I don't need to get this over to the left. Everything's where it needs to be. But what was dy over dx? -x over y. All you need to do is write it right here. -x over y. And again, you don't have to simplify. You don't have to distribute and get common denominator. And you don't have to do all that. Okay? In fact, you didn't even have to do the little bit of simplifying I did. And so this is how you do a double derivative. Now you got to keep in mind that some of the implicit differentiation problems we did were a lot longer than this. So I'm not going to have you do y double prime on every problem and they're generally going to be pretty easy problems. Okay, so here's my question to you is, I told you that if you start with the circle, dy over dx will always be -y x over y. Do you think the double derivative, y double prime, will always be this?
Yeah.
Why? Yes, is correct. Why? Yeah, what's the only thing that's going to change in the equation of a circle? The number. Is the number,
It's always zero.
and the number is not playing any significance on y prime or y double prime. So no matter what, if you start with a circle, you're going to end with this. So that's a really nice way to check your work. I'm still going to want to see that you could do this, but it is nice knowing what your answer is going to look like. Yes?
So let's say you're on like a test or quiz and like you do all your work, but let's say that you get lost somewhere, but you know like what the answer is going to be, like you've been memorized.
It's better to write it.
Can you still write it?
I would still write it, than just leave it blank, but try to get your,
Not like
yeah.
a blank, but like let's say that you worked it out halfway through and then you just can't remember how to finish the problem. But you
I mean,
just
it's
know
always
the
better to
answer.
write the answer, even if your work doesn't follow it. I mean, because you got to think these problems are multi-points, and on the AP test, the correct answer is always worth a point. But the work usually, there are things in the work that you've got to also put. And so you want to get as many points as you can get. It's always better to write it if you think it or if you know it. You always want to prove what you know on a test. All right, so what we're going to do now is we're going to look at the second day. All right, it looks like this. And besides circles, I don't really care if you know what all these curves are called or what in the equation makes them this curve. You need to know circle, okay? And there are going to be some other shapes you need to know. But this is really just here to show you like what you're actually doing. Put a picture on it. All right? And so, yeah, this page I copied it in a weird order, and so you're going to probably have to turn back in your packet. So just look for this picture, and it'll be easy to find. Okay, so what we're going to do is, this is just day 2. You actually have all the knowledge you need. I'm not going to teach you anything new about implicit differentiation, but we know that some of the problems are a little bit harder than circles. Okay, so we just need to practice it, and I want you guys to ask questions as they come up. Like, why did you do that? Or what happened to that 2x or whatever. So always, your first step is going to be to take d over dx, derivative with respect to x, of both sides. Okay, so I'm just saying, I'm taking the derivative of both sides. Okay, on the left-hand side, I have x squared plus y squared squared. What rule do I need to use to take that derivative? Power rule and chain rule. Okay, power rule because there's a power, the chain rule because what's inside is more complicated than just your plain old x. And so that derivative is going to be 2. Keep the inside part the same. This is how it's chain rule. That chocolate, the 2 is the shell melting. The chocolate, though, is not changing. The power will now become 1, although we don't need to write that. And then next, you're just going to take the derivative of the inside. So what would the derivative of the inside be? Yeah, 2x plus 2y dy over dx. And just as a reminder, you're always multiplying by dy over dx. It's not something that's stuck only to the y. It's all being multiplied. 2 times y times dy over dx. All right, so that's the left-hand side. All right, now we get to the right-hand side. Occasionally, you're going to have some algebra steps that make finding the derivative easier. We've already seen this with the problems that we did before. What tiny little algebra step would make this right side easier? Distribute that 12. Do you have to do this? No. But in my mind, it makes the problem way easier. Anytime you have parentheses in the problem, you've got to be thinking product rule or chain rule or constant multiple rule. Here, we don't have to worry about any of that. Okay, so what would the derivative of 12x squared be? 24x, and then the next one would be 24y. But since I'm taking the derivative of a y term, I've got to have my dy over dx. Okay, so last week, I didn't do this on the last problem because there was only one dy over dx, but if you remember, I circled these. And you may want to circle, you may want to highlight, you may want to use colored pens, but it's a good idea for you to really know where dy over dx is because we're going to have to move all of those terms to the left-hand side. So, what are we going to do about this? I like the 2y dy over dx. I don't like this 2x. This is weird. Not too weird, but it's in the way. So what would be a good first step? Okay, I heard divide by 2 and I heard distribute the 2. Distribute the 2 wouldn't be a bad idea. It actually really won't help us, but that much. If I divide by 2, I'm going to have to divide everything by 2. Which we could actually do. Were any of you thinking just divide this whole term? Okay. Well, what would happen to the right side if I divided everything by 2x squared plus y squared?
The dy over dx over.
I have a much bigger problem with the far right term. Now I have dy over dx all over its own function, or not function, but its own expression. Yes. Ooh, I like that idea. I'm going to just take this, and we saw this actually in the last lesson. I'm going to distribute it to both things. And I'm actually, it seems like this could be really messy, but I'm not going to simplify as I go. So that's going to make it not, it's going to make it look messy, but I'm not really going to have to do that much work. So I have the 2, x squared plus y squared, and I'm multiplying it by 2x. That's my first distributing step. Now I need to do this again. So I have plus, I'm going to do it again. 2 x squared plus y squared times 2y dy over dx. And if you can read that since I'm writing on top of the graph. All right. So what that allowed me to do is to kind of break up the problem, and we saw that in the last lesson. Sometimes you got to do that. How do you know? Well, when you can't do anything else, maybe distributing is a good algebra step you want to do. The right side remains the exact same. You need to write it. Okay, there's something called a linkage error on the AP test where if your beginning steps are great and your end steps are great, but somewhere in the middle you left out pieces where, especially when something equals something, well, you put an untrue statement in the middle of your problem. You're going to lose the point for that. All right? I didn't even know about it until I went to my conference this weekend. So just be thorough. I'm going to model everything in class how you should be doing it on the AP test, and I have been. So just make sure you're doing that as well. All right, so looks like I haven't simplified anything. It looks like this problem's more complicated. But still, know where your dy over dx is. At least now, though, I have two terms that I can easily add or subtract to get to one side, and then the other terms I can add or subtract to get to the other side. Remember, you don't just want dy over dx on the left. You want that, okay? But you want everything else on the other side. So I'm going to add 24y. So plus 24y dy over dx. And 24x over here on the right side, well, that looks good. And then this whole first chunk that I got to separate by distributing, I'm going to subtract that over. You could simplify this if you're thinking, it would have been a lot easier if I just distributed the two, or if I, simplified that. You're fine. But if you simplify and you make a mistake, you lose your points. So you just have to be really careful when you do that. All right, again, I'm going to circle these. This is not something you have to do, but I think it makes it a lot easier to know what the next step is. So what is the next step?
Divide by the first part. Divide by.
All right, so if I divide by what's in front of dy over dx, it's actually going to screw up my second term. It's going to make it more complicated. So really what I need to think is I have two different dy over dx terms. I don't want two. I want just one.
So combine like terms then.
What is that called? What is this called? Factor. That's our third step. First step is take the derivative. Second step was to get all of these terms on the left, the non-dy over dx terms on the right. Now I need to factor. So factoring here is pretty easy because you have the inside part right there. And again, you need to write the right-hand side, even if you know it's not changing. Just rewrite it. It's not going to hurt you anyway to do that. Okay, so that was the third step, to factor out the dy over dx. The reason this works is because now I just have dy over dx on the left. So what's my very last step?
Divide.
Now I divide. The last step is to divide. So when you break it down and just do one thing at a time, these problems involve a lot of writing, but they all tend to work out very similarly. So for those of you that haven't yet done the homework, you need to be practicing that. You can't just become an expert on something like this by watching me. You've got to practice it yourself. Okay, one last thing that I want to mention here is that notice that there's no dy over dx's. There's no d's on the right-hand side. Okay, if there's a d anywhere on the right-hand side, you have not finished the problem. Okay, it means more than you just didn't finish. It means you actually messed up somewhere. All right. Let's look at the next page. And we're not going to do all of this example, but we're going to do at least some of it. We'll see what we have time for. So again, you have this weird curve, not a function. And at this point, I think you guys have a pretty good idea of whether a problem's difficult, easy, or medium. So with the one we did last Thursday where it had like product rule and chain rule and lots of steps, that being hard, maybe the circle problem being easy, where do you think this problem would fall? Medium? You think in between? Yeah, I would agree. This would be a medium problem. Maybe even medium easy, because although it's not a circle, it's actually going to work out really similar to the circle problem. All right? So, start it out the same way you start out any problem. I'm kind of getting ahead of myself. That happens when I get to the third class of the day. So this is find the equation of three different lines which are tangent. We'll get to the whole idea of three in a minute. But as soon as you see that word tangent, a word should pop into your mind.
Derivative.
Derivative. So we're going to take the derivative with respect to x, and I'm going to rewrite it this time. Derivative with respect to x, both sides. Okay. I want you to finish out this problem. I will say you will have to factor, although you really shouldn't be doing anything crazy complicated. I mean, this should just be a few-step problem, and I want you to ask me questions if you have them as I walk around the room. Okay, so it looks like most of you got it. Just real quickly, what did you get for the next line? 5 y to the 4th dy over dx minus dy over dx minus 2x equals 0. Okay, what did you have to do before you factored out the dy over dx? You had to add that 2x over, okay? You had to add the 2x. All right, so now when you factor out dy over dx, you had 5y to the 4th minus 1 equals 2x. Let me write the final answer over here. dy over dx should have equaled 5y to the 4th minus 1 all over 2x. Okay, so that's nice, but I really haven't even answered any of the problems. Oh, yeah. I'm just trying to keep you guys on your toes. All right, I'm just kidding. All right, so I'm going to box this, not because it's my answer, but because it's important, and I know I'm going to have to come back to this. All right, so then A says find the equation of 3 different lines that are tangent to the curve at x equals 1. We haven't done this yet. Every other problem we've worked before now, there's only been 1 tangent line. Why in this problem are there 3 tangent lines at x equals 1? You might want to look at the graph.
Vertical line. There's three points at which.
Yeah, this is not a function. Remember, functions, there's only 1 point when x equals 1. Now there's 3 points. All right, so these all have their own slope and their own y value. So we got to find that. Okay, this is just algebra though at this point. So I have my x. I have a slope function, slope generator, but I don't have the specific slope and I don't have the y. In fact, I can't do anything until I get the y, because look at this. If I were to plug 1 in for x, what do I plug in for y? I don't know. So which function, I keep saying function, and I really should not be, because none of these are functions, the derivative or the original equation. But which one of these are we going to use to find y? The original. Okay, so that really has to be our next step. So I have y to the 5th minus y. I know that in this problem anyway, x is always going to be 1. Now this is an algebra problem. Okay, y to the 5th minus y. Well, this is interesting. 1 squared, that's just 1. What happens when you add 1 to the other side?
0.
You get 0, which is nice. I want that side to be 0, because now I can factor and then set my factors equal to 0. So what would be your first step in factoring here? Yeah, factor out a y. So now I have y to the 4th minus 1 equals 0. Can I continue factoring? Okay, let me just say this. You can. What can you do? Difference of squares. So I'm going to have y squared minus 1, y squared plus 1. Can I factor further? Yep. Y minus 1, y plus 1, although y squared plus 1 does not simplify, and it's actually going to be totally useless in this problem, because when you set y squared plus 1 equal to 0, you end up trying to take square root of a negative, so there's no good solutions. But I have 3 good ones right here. I have y equals 0, I have y equals 1, and I have y equals negative 1. We don't need the graph for this problem, but let's the graph is going to be a good check. So go back and look at the graph and see, do those y values make sense?
Yeah.
Positive 1, 0, negative 1. Yes. Okay, so that's a good sign. All right. So now let's go ahead and take these on a case-by-case basis. Okay, so on the first one, yeah.
Explain why you scratched out the y squared plus 1 again.
All right. When you set y squared plus 1, or anytime you have a sum of squares, this is actually always going to work. When that equals 0 and you subtract that 1 over, look what happens with the square root. You try to take square root of a negative number. That's an imaginary number, and I already told you guys, good thing about calculus is we're not going to really deal with imaginary numbers. There is a time and a place for that to be in calculus, but we're not going to be doing that. Definitely not in a problem like this, where we're talking about actual points. Good question. All right, so first case again, x equals 1. Let's just go ahead and let's let the first case be y equals 0. Well, I still don't know what my slope is. But don't I have a slope generator?
Just plug in the x, y value.
Plug in the x and y values. So I think that was 2x. I'm going to rewrite it right here. So that's going to be 2 times 1 all over 5 times 1 to the 4th minus 1.
When you're writing that, like dx over dy, would you do d0 over d1?
No, you don't need. I'm really not right. I'm writing in because, you know, I'm not so much concerned about the derivative equation. I'm concerned about the slope of my line.
Okay.
Yes.
Should the bottom parentheses be a 0? Yeah.
Yeah, it should. Man, you guys are on your toes today. That's good. 'Cause apparently I'm not. That's okay. All right. So what does this whole thing simplify to? Negative 2. All right. So let's go up to the equation and let's just see, or sorry, the graph. Let's just see, does this make sense that my slope at y equals 0 and x equals 1, does it make sense that the slope is negative 2?
Yes.
Yes. So again, we didn't need the graph, but it definitely helped. Okay, this part though is easy. We've been doing this. Well, it's easy if you can write it. We've been doing this since the first time we talked about derivatives. Y minus 0 equals negative 2, x minus 1. No need to simplify. That's your answer. Okay, so what I want you to do now is I want you to find the other two. You're going to have to go through the steps, though. Okay, don't try to shortcut. There are some shortcuts. All right, but go ahead, find the slope, write the equation, then do the last for your very last y value.